Okay, so good morning. And today we will actually formally define the Lorentz group and from that and representations of Lorentz group. Don't worry if that doesn't make sense to you. I may or may not tell you what a representation is, but we will see examples of representations. And we are physicists, so examples are good enough. Okay, so I mentioned something called so let's first do a recap. I mean, we saw that uh, Lorentz boost uh, is a, okay, and but we didn't do like looking at Maxwell's equations, but we rather did a thought experiment and figured out corrections to order u by c, and then just use exponentiation. So the fancy formula was this: lambda was equal to e power little lambda. But the most general little lambda for a boost was something like this, right? 0, uh, minus phi 1 or plus phi 1, don't worry about that. Phi 2, phi 3. Okay. We also know that rotations can be written are also symmetries. I mean, that's manifest because Maxwell's equations are written in terms of quantities which transform nicely. Rotations are obvious symmetries if you wish. So we can write those guys as, let me write R with underscore R as follows, as a 4 by 4 matrix. Here this bar means just 4 by 4 matrix. Okay, and so we know that and further this can be written as exponential of for something which I'll call A bar for the moment. Okay, so A bar again is a 4 by 4 matrix. So A bar would be 0, 0, 0, and the usual antisymmetric matrix 3 by 3. Okay, so I'm just so this one just says that the zeroth component was a scalar, right? Is I mean phi or x0 they were scalars, so it just generalizes that. And this one just says that they don't transform under rotations; they are scalars. Okay, and one is e power 0. So this is how it works. Okay, so this is block diagonal. Okay, so this is a 1 by 1 block, and that's a 3 by 3 block, and all others are 0. Is this notation clear? Okay, so now I will give a slightly different, so I'll introduce something called Minkowski space. Okay, so it's just a linear, it's a linear vector space. Okay. And which is 4-dimensional. Okay, so let's give it some notation. We'll write some n like this. Okay, okay, but it has a strange, it has an unusual inner product. Okay, it says something like if you give me a norm of a 4 vector, that would be v0 square minus So that's what it is. We can write this, so we can also write this as follows. We can write this as V bar transpose dot something which I'll explain, which is a 2 by 2 thing, which we call the Minkowski metric. V bar, where V bar for me is V0, V1, V2, V3. Okay, and eta is called the Minkowski metric. It's a diagonal matrix, but with 1, minus 1, minus 1, minus 1. Called the Minkowski metric. Is this clear? Very easy to check how to go back and forth between this. So this eta will be, and here is some notation. We will use mu, nu, Greek indices, mu, nu, rho, sigma, tau, etc. These run from 0, 1, 2, and 3. I, J, K Roman guys, they run from only the space indices. Is this clear? Because this is just standard. This is a notation that we will follow. And there's an important remark, which is that not all books follow our convention. Okay, and some choose to put the minus sign only with V. So the norm will be minus of what we wrote. Some books choose norm of V bar square equal to minus V0 square plus, let me just do it. Yeah. Okay. So for in this convention, the Minkowski metric is minus 1 plus 1, diagonal, of course, plus 1. So this is called, so there's a simple way of remembering this. We say this is mostly minus convention. Okay, and this is mostly, what should this be called?
Plus.
Okay, mostly plus 1. Okay, so whenever you read a book, so check the convention used in any book that you study. So this is the thing, and we also said that we'll call this, we called objects like this, we call them 4 vectors. Okay, is this clear? So this is just kind of putting things into perspective, and so now I will define Lorentz group in a slightly different fashion, which is mathematical, not what we had done was use some kind of physicsy approach. Okay, so now we will define Lorentz group. Definition, we can define. The Lorentz group is the set of linear transformations that preserve the Minkowski norm. So what do we mean by that? Is suppose we have, so let's write a linear transformation. We'll write it like this: V prime is say lambda is any 4 by 4 matrix, not necessarily a Lorentz group, equal to like this, and we have the condition that norm of V prime square should be exactly equal to norm of square. This is the condition. Okay, and the reason to do this is similar remark is this is how we could uh, we obtained the orthogonal group. Right? Isn't that right? Okay. It preserves the norm of a vector in 3D or R3. Okay. It's not M. Okay. So R3 with standard norm. So that's what this is. So if you just write this and use this, so exercise, show that. Okay. Condition can be written as follows: implies M transpose dot eta dot M equal to. Okay, so now you can see that if I replace eta with Kronecker delta, that becomes, okay, if eta, instead of eta we had Kronecker delta, what do we get? What kind of matrix would that be?
It's a usual
Euclidean orthogonal matrix. Orthogonal. So M would be orthogonal. Okay. So this generalizes the usual orthogonal group. Okay. So you can verify. And let's call this star. You can verify that all matrices that satisfy star on a group. It's very easy. It's the same. You will see that it's just almost identical to this. Okay. And so we should give a name to this. Okay. So this group is called O1, 3. Okay. So let me more generally O P, Q is the set of matrices M that satisfy M transpose dot eta P, Q dot M equal to eta P, Q, where eta PQ is diagonal with P plus 1s and Q minus 1s. Is that clear? So our example would be eta 13 is what I call eta. Okay, so eta 13 is what we call eta. Okay, so it's still called the orthogonal group, but it has with some signature. PQ is called the signature. Okay. How many pluses and how many minuses? Is this clear? So this so we have a group called O13. So first one is determinant of M. What do you think determinant of M will be? Plus or minus 1? Okay. So this is one thing. SO13 is the subgroup of matrices n such that determinant of n, what should I say it is?
1.
Plus 1. Okay. So now we can still ask what are the matrices which we can construct which determinant equal to -1 examples. Okay, we'll do examples. And it turns out we need only 2. Okay. So we'll call those matrices. Okay. So let T, okay, T which belongs to 013 be the following diagonal matrix: -1, 1, 1, 1. Okay, so let's see what this would be. So let's see how it acts on T acting on the x vector. What does it do? X is just the space-time thing. x0, x1, x2, x3. Okay, so what does it do to x0? It changes sign. Doesn't do anything to the others. Okay, so what is this operation? What is x0? Up to a fact.
Time reversal.
Yeah, so we'll call this time reversal. Okay. Then there is parity, which we'll write as follows. Again, diagonal matrix. There's nothing to time, but flips say all of the coordinates. So this is parity. Okay. So it's easy to check that det t equals to det t equals to -1. Okay. So what happens is that I will draw a picture now. So yeah. So you can see that p times t or equal to t times p belongs to O SO13. Right? Because determinant of p is -1, determinant of t is -1, so the determinant. So it belongs to SO1, 3. Okay. But the point here is that, but this operation, if you go back and see, it involves, it's like both time reversal and parity. Okay, so what we do is the following: is that we break up matrices. So yeah, just yeah. So yeah, yes. Let me draw proper straight lines. It's a different color. So let's say that this side is det greater positive, greater t positive. Okay. So so right side will be SO13 matrices. So I'm breaking up all the O13 matrices into 4. I'm partitioning them into 4 things, and the one which is which I will write as SO13 plus and SO13 minus is the following. This has an additional condition. Okay, this is SO13 we know already, plus why didn't it change sign? Okay, so the plus refers to M00 being positive. Okay, your minus means not determinant. Determinant is already there. Okay, so what is happening here is that so matrices here would be having time reversal. Okay, so this matrix is SO13 plus. Okay, so this can be written as equal to T acting on SO13 plus. Okay, so all the other entries I'll start writing now. So things here, so the matrix here would be PT times SO13 plus. And oh, I'm sorry, what did I write here? Sorry, this is wrong. So what is it I want? I want determinant equal to -1. So
So in the fourth quadrant, the determinant is turning out to be -1, right?
yeah, so that's where I made the mistake. So it should be
Yeah, that's why you
just
should write
PT here. Now I'm okay.
Yeah.
Okay, now that's what I was getting confused. Okay, here what we will get is a -1, but so this will be P times SO. Okay, is this clear? So these are the discrete guys. So thank you for this correction because I was just checking. And PT should be determinant plus one. Okay, so this is all we are seeing. So below this as M00, so here also M00 is greater than 1. Here M00 is less than 1. Okay, so these are the four kinds of matrices. And so is this picture clear now? So it's just four quadrants, but actually
What
there
is
are
M00?
M00 is the so M, if you write the matrices, so it will be M00, M01, M0. It's a matrix element of the matrix.
Okay, okay, thank you.
So it's this guy. Okay, so that's all. Okay, so the thing here is what is the Lie group? Okay, so the Lie group. Okay, and so all elements of it can be written as exponential of the Lie algebra. You see, all that hard work we did, it tells us that we are able to say these things in a very, very simple manner. Okay, so that's it. Okay, so this is what it is. There are some properties of these various things. Those are algebra, simple algebra, and it's given in problems as well. Okay, is this clear? Okay,
Yes, sir.
so SO1 3 plus is usually called the orthochronous. Orthochronous. Chronous means time, so ortho, that means it's preserving the direction of time, right? If something was in a minus, right, it's changing the direction of time. So orthochronous, special, determinant equal to +1, time preserving, uh, special, orthogonal matrix. Okay, with signature 1, 3. But I won't say that. Is this clear? Okay. So this is the Lie group, and instead of saying all these things, okay, or orthogonal matrix, or we can say Lorentz element, not matrix group. Okay, so usually I use a definition here, but so this is a mouthful. So I abuse terminology and refer to uh, SO13 plus as the Lorentz group. Okay, is that clear? Okay, it's just some abusing of terminology because I can't keep saying it's a mouthful. Orthochronous special orthogonal group, it sounds very long. So okay, so this is the setup, and you can check that that's this beautiful group, etc. Okay, and so again there will be the properties of four vectors. Okay, are given by additionally specifying behavior under parity and okay. So we already fixed the behavior under parity for E and B. So exercise. Okay, how do E and B transform under time reversal? Okay, so you can even do it in the following way. You can think of, a point charge in motion. So under time reversal, its velocity will flip sign. So what happens? You go ahead and ask and work out what it does to B and what it does to E and stuff like that. And you'll find and go back and check that you can assign it in a nice way. So, should rho be, so the question is, so for instance, let me say, rho is invariant under T. J goes to minus J under T. Using this, you try to assign, okay? And nabla goes to what? Nabla. Nothing happens with that. So you can fix E and B. So just do that. It's just sort of fun. Okay? So is this clear? So let's move on. I'm done with the formal part of the Lorentz group. But now we want to see physical implications of the Lorentz group, but really we need to only study Lorentz groups. So we'll start doing some simple experiments. Okay. So we'll let us consider. We'll go back to the two frames A and B, if you remember. Okay.
So let us consider is that A.
Okay. And for simplicity, I will just assume that there's only X direction, so the boost. Okay, for simplicity. Focus on a boost in the X direction. Okay, so in frame A, delta X equal to 0. Okay, so particle is not moving. Of course, delta Y and delta Z is also 0, but okay. So that's not relevant for us. Now, How does this appear? Okay, so so we can ask what is delta x prime. Okay. Instead of doing that, I will work out what delta x by delta t prime is. We know how these things transform. So just write that. This will be equal to c, might be minus signs. Okay, you have to do an order. So let's do mod of it. So let me not sine hyperbolic phi on delta t. Okay, so this is what we would say is the speed. So we will say that particle, the particle is moving with speed. What speed? Okay, so delta t is cancelled. So if you wait, right? So this would be tan hyperbolic c times tan hyperbolic. Okay, I just briefly mentioned this. I didn't show you this thing. So you can see that if you take care of signs and all, so sine of phi 1 also. So in particular, so that's what this will get. So this is the key point. Okay, so speed is not phi. Okay, so this is the okay. Is this point clear? Okay, so there is some definitions people do, some standard notations. Beta, and let's drop the subscript 1 because that's only a boost. So beta is defined to be u by c, which is equal to tan hyperbolic phi. And gamma is defined to be cos hyperbolic phi, which is equal to, you can compute 1 by. Okay, so this is standard textbook notation. Okay, so for instance, so if you add x prime, I pulled out some, let's say it will be something like this, x minus 2. Okay, so this gamma factor is there. Okay, but it's also interesting. You can see is that gamma is 1 plus order u square. U by. So you can write out what is t prime. Okay, you can do this. So now we will do a second experiment. Actually, let me write this formula fully. Okay, because I want to emphasize something. I'm writing. I'll explain what x parallel is. Okay, so this is the full Lorentz transformations. Okay, where Okay, x parallel is the uh, is along is parallel to the is parallel to the direction of the boost. So if you give me any vector x or any vector, the three vector x, and you have given me a vector, you can see that the following holds, that x parallel is nothing but yeah, x parallel times has to be along u, but divided by magnitude of unit vector. And then x perpendicular is a vector which is orthogonal to the direction of u, whatever remains. So it is just x vector minus, remove the parallel component, which is x parallel, and it's along u by. So these are definitions. Whenever you give a given direction, you can do this thing. Okay. Is this clear?
Yes, sir.
So you can decompose. So that's what I have done. So x here could be any vector, but I'm using it for displacement. Okay. So this is the general setup. And but there is a important thing which follows from. So we saw that u in the example was u by c rather was tan hyperbolic of phi. Okay. And, oh, I don't want this phi. I wanted this phi. Okay. So if you plot now. So, So phi goes from minus infinity to plus infinity. But you look at u can only is bounded by plus 1 and minus 1. So if you plot this function as you change phi, you will see that it asymptotes goes to 0 here. Okay. So this is the famous statement that the speed cannot. Okay. So this is related to the fact that u by c is bounded by 1. It can never exceed the speed of light. Is this clear? So this is some very, very interesting consequence. Okay. So and the third one which I mentioned again last time is addition of boosts. Okay. So suppose we follow a boost with rapidity, boost along x direction with rapidity phi 2 with rapidity phi 1. Okay. we do not get a boost. Okay. Suppose we followed a boost along x direction with another boost, okay, along x direction. You can check that it is another boost with rapidity additive, okay, so that you can check. But for this, what you will see is that okay, so this you check in PS2. However, if the boosts are parallel, okay, rapidity and not velocity. Okay,
So
so this
you
is,
mean parallel Lorentzian boost
yeah, so you do a
add up
Lorentz boost
to
along x direction with phi 1, then follow it up with a Lorentz boost with along x again with
yes,
phi 2,
got
then that is equal to a Lorentz boost along x with rapidity phi 1 plus phi 2.
yes sir. Got it.
Okay, that's what I mean. Okay, this is non-Galilean. Okay, this is Galilean. In Galilean thing, we would have said add the velocities, right? So this is not the thing. So if you ask what this implies, you will see that so let's say that okay, then if you add so addition, so this is the final composed velocity. Okay. This should you will be C tan hyperbolic phi 1 plus phi 2, which if you work out in terms of these things will be u1 plus u2 divided by 1 plus okay. So you can see that this will be, if either one of the u1 or u2 is small, this will be approximately u1 plus u2. If say u1 by c is much less than 1, or u2 by c is much less than 1, or both. Okay, so that is the Galilean. So this Galilean. So again, we see that Galilean boosts hold only in the limit of small velocities. This is the key thing. Okay. Okay, very good. How much time do I have? Okay. Okay, so what we'll do is today now we'll just I'll give you some other, so we'll see examples of four vectors. Okay, so we already seen one, so we saw that a 4 vector was phi b vector a. Okay, so I'll give you a second one. It's called the energy momentum. So we'll write that as p, small lowercase p, equal to okay. So what is so the thing is, so the vector part is just the usual three vector for momentum and 4 vector of a particle, say. Okay, so we can ask, and now dimensionally I have to divide by c, so that E and C have the same energy, the same dimensions. Okay, so that we do that thing. And so we can ask what is the norm of this 4 vector square. It becomes E squared by C squared minus B dot B. Okay. So this is, by the way, equal to NC. This is a Lorentz, this is a scalar. Because it's just a norm of a 4 vector. Okay, and what is that? That turns out to be this thing. So we can rewrite this whole thing. So this gives you the energy momentum relationship, and to see that this is not something I have cooked up, we can rewrite this as I did E square minus C square P dot E equal to, or E square equal to C square P square plus NC N square NC square whole square. Okay, so let's look at this formula. When P equal to 0, E equal to mc square. Okay, when P is not 0, okay, then we can see that E, if you expand it as a power series in P square, will go like mc square plus P square upon 2m plus order P over 4. Okay, P square is nothing but P dot P. Okay, so you can see that this, so in the limit of small momentum, okay, key point is, in the limit of small momentum, you see that this is, in at least in Newtonian mechanics, this is a boring number. I mean, it's just a constant, so there's no zero of the constant. So we can forget about this for the moment. So it just says that the energy is just, of a free particle, is just P square upon 2m. This is something which we know. Okay, so now this kind of gives you evidence that this m that we get here is precisely the mass which appears in the kinetic energy for a particle. Okay, so okay. So of course E equal to mc square is a very, very famous formula. I call it the t-shirt formula because you don't have to understand anything about special relativity. And there is this famous t-shirt which says E equal to ma square, E equal to mb square, and E equal to mc square. And you strike out, a and b square and then say that is the correct answer. But we know better. For us, this is the real answer. Not only for P, this is the answer which is given by special relativity, by taking Lorentz transformations seriously. Okay. Okay. So this, so in, like, let me just repeat, in Newtonian mechanics, we associate zero energy for a particle at rest. Okay. So what we call energy will be E prime, which is E minus mc square. Okay. Exercise, you can work out what the P power 4 thing is. It's a binomial theorem. But however, in relativistic mechanics, or at high energies, okay, particle number is not conserved because of pair creation and things like any processes that are. Okay, here we need to use mc square as the energy needed to create this particle, the minimum energy to create a particle of mass. Okay, so for instance, you will see that we can have, E plus, E minus, electron and a positron. They have the same mass, but they have opposite charge. They can decay to gamma. Okay, but if you look at this system, the smallest energy that is possible, the energy here should be greater than 2 or equal to 2 me square. Okay, so whatever photons you get here, their total energy better be, at least greater than 2 me square. Is this point clear?
So basically, you're saying that as MC square is a system,
Hmm.
that's why when we are dealing with, Newtonian mechanics,
We
okay,
don't worry about
low
creation of
velocities.
particles. There you're given, the
Sure.
particle has been given already, so it doesn't make, so
Yes,
we don't worry about.
in rigid bodies, like
Yeah,
we
yeah.
don't have
We don't have
breaking
to
up of the
explain.
particles.
Yeah, we just don't have to explain where the mass came from. There's nothing
Oh,
about
yeah.
that. Okay.
But
So.
when we go down to
Mhm.
like lower scales where the
Mhm.
particles are breaking apart as something
Mhm.
particles are getting created,
Yeah.
then we need to consider that energy. Right.
Yeah.
That's
Correct.
what you mean by saying that the particle number is not conserved.
Yeah. So I mean, like for instance, neutron can decay into a proton plus electron plus neutrino. So you can see that you started off with one neutron, ended up with 0 neutrons, but you got one
Mhm.
proton, one electron, one neutrino. You got 3 particles. That's a classic example. Okay.
Right.
Okay. Uh, so I think I just stop here. So that so this is the first example that we have. But for instance, there are more complicated objects. Complicated in quotes because objects that form 4 vectors. Okay. So what is it? You can ask. We have a 3 velocity. What is u? Can we make it a 4 vector? Then what do you add to it, right? So these are the questions that we need to answer. We will see this in the next lecture, how these things come about, etc. Okay. So, and one more point here is that we saw that so this momentum here is not bounded. Velocities we will see will get bounded, but not momenta. Momenta go from minus infinity to plus infinity, usually. Okay, so I'll stop here and pause for questions.
Sir, when momentum was non-zero, how did we get the expression for energy as mc square plus p square by 2m plus
Ah,
5
yeah, yeah,
p2?
yeah. Good. So, no, this box formula is the correct formula. Okay.
Mm-hmm.
So now when I do e square, I have to take square. You can see e square is this thing. So you have to get e, I have to take the square root,
Yes,
right?
sir.
So then you
Yeah.
pull out an mc square and it will become 1 plus uh, p square by mc whole m square c square. You would expand that as a power series, binomial theorem. So this is the first non-trivial term. This is a binomial expansion.
Okay.
Okay, so maybe I will write it here. Multiply everything out. The most interesting thing that happens is that this is equal to mc square. And the nice part is that the c disappears. Okay? The c squares cancel and m cancels one factor of n square. So this is what we get. Okay?
Okay, sir. Thank you.
And it's kind of pleasing because we do not want C to come in some non-relativistic, in Newtonian mechanics. We don't want C to be there, and of course, it has to cancel, but it cancels. Okay.
Yeah. Thank you, sir.
Any other questions?
How did we get norm of P equal to MC?
So it has to be some constant. Okay. I'm just calling that constant MC whole square. That's the definition of m. But I'm showing you that that is equivalent to the mass. This formula tells you that this is the same as the mass we would have defined in Newtonian mechanics. Okay. A priori, we don't know that. Okay. So I would have just written, I could have written it as some c, is some constant. But what I'm saying is to make it match with Newtonian mechanics, that constant better be mc whole square.
So at graduation level, we learned that that mc square term was defined to be that constant because we wanted the energy and momentum to be conserved for some
No.
collisional experiment.
It's simpler than that. It's like what I said. It's a norm of the 4 vector, which should be a constant. Okay. It's simpler. Yeah, there are a lot of things people say. I mean, but in my mind, this is the correct way to think about it. Okay. There are many books I don't agree with how things are presented. I don't want to criticize. You agree, right? This just tells you, it puts everything in the same footing. Okay. I'm not
Yes, sir.
I'm not proving that energy momentum is a 4 vector. I'm just saying that is the 4 vector. End of. Okay. Any other questions?
So just a comment.
Mm-hmm.
So in time reversal, u gets to minus u because there is a d by dt in
Yeah.
velocity, and nabla doesn't change because there's only d by dx.
D by dx, exactly.
But in quantum mechanics, we get momentum by doing d by dx. So in time reversal, doesn't seem to change. It's not intuitive, right?
Yeah, you go back and look at but then you have to go back to Schrodinger equation. Absolutely correct. But in Schrodinger equation, under time reversal, psi doesn't go to psi. Psi goes to psi star because there's an I in that thing. So I also changes sign. I square, I star. Okay. So under time reversal, psi is not psi. Go back and check. If you want your equations to be invariant, you have to do that. Okay. Good point.
Yeah. So del by del d, E can't be negative. So that
Yeah.
Okay.
Yeah. Okay. So
Sorry.
no, not sorry. No. It's a different set of equations, but it will work, and it works because I goes to psi star. So there's complex conjugation and Schrodinger's equation is nice. I mean, there is an I which is square root of -1 in the equation, right? IH power d by dt, right? So it works out. Actually, beautiful question. Okay, so let me just stop recording. You can ask questions still.